First, I will show you a simple example of counting sort. And counting sort is a sorting algorithm using counting. Look at this array. It has only zeros and ones in the array. Then the output should be like this. And there is a very simple method to get this. What would it be? Anna, do you have an idea? No idea? 윤영주, any ideas to sort this array very fast? We can use insertion sort, heap sort, or merge sort. But we know that insertion sort takes big O of n squared time, and heap sort and merge sort take big O of n log n time. But there is a way to sort this array in linear time, big O of n time. What is it? That is, let's use two counter variables. And this variable counts the number of zeros. And this variable counts the number of ones. And because their sums are n, we only have to count only once in this case. Then we scan this array from the left to right and count the number of ones. What is it? There are 5 ones. And after the scanning, 5 is stored in this variable, in this counter variable. Okay? Then sorting is like this. Write 5 ones and 3 zeros in the output array. Okay? It's done. Then let's try a more general example. In this array, there are more numbers. What is the smallest number in this array? 0. And what is the largest number? 5. Yes. So okay, it's here. We create an array with 6 entries from 0 to 5. And then we scan this array from the left. First, it's 2. So we increment this element. And then it's 5. We increment this. And then 3. 0, 2, 3, 0, 3. So after the left to right scan, we have a counter array like this. And it says there are 2 zeros, no 1, 2 2s, 3 3s, and no 4, and 1 5. Okay? Then we just fill the output array using this counter array. 2 zeros, 2 2s, 3 3s, and 1 5. Yes, it's very, very simple. And I think it's one of the simplest algorithms you've learned until now. And it's very fast. Okay? Okay. Then some students might ask these kind of questions. Then this algorithm beats all the other algorithms. It runs linear time and it's very simple. Okay? Then why did I teach you different algorithms? Then let's check out the running time carefully. What is the running time of this algorithm? 이희준. What do you think is the running time of this algorithm? Theta of n, and n is the number of entries in the given array. Yes. Is that all? Look at this array. Look at this counter array. What should we do for the first time before we use this counter array? We should initialize every entry as 0. So we have to take it into account. And then what's the size of this array? So usually we denote it by k. K is the range of numbers in the input array. The maximum element subtract from the maximum element the smallest element. In this case, this range is smaller than n. So we can say it is theta of n. But let's consider a different array like this. Like this. In this case, n is small. We have only 4 elements, but k is very big. So k is the dominant factor, so its running time is k, theta of k. So this counting sort is effective only when k is small. And it runs in linear time. That is important. But sometimes, from the context, you may know that the number of the range is very small. If it is a bit array, we know that k is 2. So in that situation, you can safely use this counting sort. Okay, then I'll explain counting sort a little bit more. This is a simple version of a counting sort. Usually, counting sort satisfies stability. The definition of stability is like this. In the input array, there can be same elements. For example, 2 appears twice, and 3 appears 3 times. And being stable means when they are sorted, the orders of same elements should be satisfied. For example, this 2 comes from this, and this 2 comes from this. At first, there is no difference between these 2 elements because they are the same values. But sometimes they have satellite information, such as these might be names, but their student IDs are different. Then they can be considered a different element. So to satisfy this, counting sort should be changed like this. The algorithm is the same up to calculating the count array. So this count array stores the number of occurrences of each element. And then we create a C prime array like this. So for a minute, try to understand the meaning of the C prime array. Actually, C prime array means, in this case, this means the occurrence of number 2 in the original array. But in the C prime array, the occurrence of integers at most 2. So 0, 1, 2. Look at this. There are 2 zeros and 2 0 and 1s, and 4 0 or 1 or 2s. And if it is 3, it's 3, it's 7, 7, 8. So this is the accumulation up to that number. Okay, then we initialize an output array B, and we scan the original array backward. And it's 3. Then we check out the C prime array 3. C prime array at 3. And it's 7. So we place this element in the 7th place. Does it make sense? Yes. The 7th means there are at most 7 elements less than or equal to 3. So 7 is the perfect place for this number. And then we decrement the value by 1. It means if we come across 3 again in the input array, it is later stored at 6. And let's see. The next element is 0. So we access the zeroth entry of C prime, and it's 2. So we place 0 in the second place, and then we decrement it by 1. Okay, next we see 3 again. Then we access the third entry in the C prime array, and it's 6. We store in the 6th place the 3 here. And then we decrement the value by 1. In this way, we can store all the values from the input array to the output array. Okay. Then, by scanning backward, we can guarantee that their orders between same entries are preserved. Look at these 2 3s. The latter 3 is stored here, and the former 3 is stored here. So their orders are preserved in the output array. Okay. I explained the counting sort using an example. And let's understand it perfectly using this pseudocode. So let's read this pseudocode step by step and try to understand the meaning with the help of the examples. And more exactly, it's theta of k, because exactly k. Big O of k is fine. So first we initialize the counter array with zeros, and its running time is simply theta of k. And then 조정환. Yes. What's the meaning of the next 2 lines? Lines 3 and 4. So lines 3 and 4 is just counting step. And what's the running time of the counting step? N. Why N?
Because the number of elements is n.
Yes, it's theta of n because of the scanning of the input array from left to right. Or you may scan from right to left. Or you may scan in any order. Once every element is counted once. Okay, then next, 윤호상. Okay, can you explain the lines 6 and 7? Yes, it's accumulation or summation. So C0, so actually this is the same as the C prime array in the example. But if you see this carefully, we don't use a different C prime array. We can use the C array, we can reuse the C array rather than using a new C prime array. In this case, 2 is added to 0. Then it becomes 2. Okay, then 2 is added here, and it becomes 4. And 4 is, so until here, the first half is a C prime array, and the second half is the C array. And then 4 is added to 3, 7 is added to 0. So C prime array can be stored in the C array without any errors. So this is it. And then what's the running time? Yuno-san. What is the running time of lines 6 and 7? Theta of k. Yes, simple. Look at this. This is, look at the index only. It's k and k. Park Sung-hyun. Okay, can you explain these 3 lines? So we scan backward. We scan the input array backward. So this index shows this. And then it looks quite complicated, but this line is used to find. So this nested array of access is to find the location of the upper array where AJ should be stored. And this is the decremental operation of the C array. And then what is the running time of these 3 lines? Theta of n. Yes, we scan the input array backward once. So its running time is theta of n. Then let's add all these values, k and kn. So the total running time is theta of n plus k, where n is the number of elements in the input array and k is the range of input elements. So if k is quite small, it means if k is bounded above by n, that is big O of n, running time becomes theta of n. So use counting sort if the range of the input is very small. It's very fast. Okay, there are some exercises related to counting sort. Okay, then I will explain another sorting algorithm, radix sort. So try to understand the radix sort by looking at this example carefully. Or you don't have to look at this example carefully. Just look at this example, and then you will recognize the radix sort. But it would have been better if you explained more detail. So these numbers are 3-digit numbers, and each digit is called a radix. So we have 3 radixes. And first, we can sort using the first digit. Then this is the digit. In this case, the first digit is 3. And the second group is consisting of 4 in their first digit, and 6, 7, 8. So first they are sorted using their first digit. And then in each group, they are further sorted by their second digit. So in the second radix sorting, we don't look at the first digit. We look at the only second digit. And finally, we look at the last digit and finish sorting. And it's quite straightforward, okay? And you can understand easily. But when you program it, it's quite boring. In this, you have to maintain the number of groups. So when they are small, it means you have a lot of groups. So maintaining a lot of groups is quite cumbersome. But there is a simpler version, like this. Instead of sorting them from the bigger digit to smaller digit, we do it backward. First, we sort the values using their smallest digit. Then they are sorted in this way: 0, 1, 3, 4. And then look at the second digit. And finally, we move to the first digit, and then sorting is completed. And the algorithm is very simple, but it looks quite strange, right? Looks strange. Why? 한상현, what could be a problem if we sort in this way? Yes, correct. So we sorted using this digit. But if we see only this, their orders cannot be used. Right. But can you explain more exactly when does it happen? Their orders are changing. look at this, it's 9 and 5. So 9 in here, this is before this. But if their values, the values in the second digit are different, we don't have to care about the last digit. So when does the problem occur? But if their values are different, we don't have to care about it because they are sorted using only these numbers. But sometimes we have to see the smaller digit. When do we have to see that? Yes, when they are the same. In this case, if yes, this is 1 and this is 3, and they are the same. If they are the same, if we don't see the smaller values, they can be mis-sorted. Right. 주정한, 현은율. But you all know how to solve this problem. How can you solve this problem? 정명수, can you suggest an idea to solve this problem?
비교할 때 다 두 번째 거 비교할 때는 세 번째 거 같을 때만 체크해서.
So look at, if they are the same, look at the third digit. But there is a better solution. And I taught you how today. Yes. So the important thing is, if their orders are preserved, then it's done. So when we sort this radix, if we use the counting sort, the orders are preserved, so we don't have to see other radixes. That's the point. So in this example, going into more radix doesn't make a big problem. But if we have more radixes, then sometimes we have to see almost all radixes. So using counting sort is the answer. Then let's look at the pseudocode of the radix sort. It has only 2 lines. From 1 to D, D is the rightmost radix. 1 is the rightmost radix. Radix 1, radix 2, radix 3. You have to see this way. And use a stable sort and counting sort to sort array. And then the running time of radix sort is theta of D times n plus k. And D is the number of radixes, and n plus k is the running time of the counting sort. So if k is big of n, and this becomes linear, and if d is constant, such as 3 or 5, then the running time of radix sort becomes theta of n. Okay. Until now, I explained counting sort and radix sort, and the running time of radix sort is theta of d times n plus k. N is a fixed one. It is given. But I will explain d and k can be changed like this. Look at this. These are 4-digit numbers. And a natural way of applying radix sort can be like this. Every digit becomes a radix. Then, what is the number of radixes? 이종하. 이종하? 4, yes. And 이종. What is the range? Size of range? 4? I mean K. 이동. You did. 박영호. 문경식. 8? Yeah, 8, fine, but in general, it is from 0 to 9. So K can be 10. Okay, in this case, it's 4 and 10. But if we think them in a different way, in this case, there are 2 radixes, and the K is 100, from 0 to 99. So we can adjust D and K to maximize the performance. Look at this. Every number can be represented by binary systems. So now, from now on, let's look at their binary representations. Then n is fixed. N is the number of values. And let's think the longest integer can be represented by b bit. So b is the maximum number of bits. Then we can divide the bits by all bits. Then each all bits becomes a radix. So there are b over all radixes. So all is the size of radix. Okay? Then what is the range of each radix? Because there are all bits, the smallest number in each radix is 0, and the largest number is 2 to the r minus 1. So the range is 2 to the r. So we get the running time is theta of b over r times n plus 2 to the r. So if we change the value of r, the running time is changed. And look at this term. This term becomes smaller as r increases. So as R increases, the number of radixes is reduced. But the range increases as R increases. So we have to find an optimal value of R to minimize this running time. And there is some explanation about this. And the answer is usually log n. The R should be around log n. Then the running time is minimized. So I will not explain this in detail. But if you are interested in this, read this material. So this is the end of sorting algorithms. So we learned a lot of sorting algorithms. And sometimes one sorting algorithm is good and the others are bad. But in other cases, another sorting algorithm is good. So you have to find a best sorting algorithm which is best in a certain situation.